So to review for Unit 1, we'll talk about these three different sections: chemistry, water, and carbon. Okay, question number 1. All these are very, very good test questions. What is the difference between an atom and a molecule? Or what can you tell me about the characteristics of a molecule or what makes up an atom? So an atom or a molecule is made up of two or more atoms. And as far as an atom we know is made up of protons, neutrons, and electrons. Okay, now how about an example? What is oxygen? Is oxygen an atom or a molecule? And the answer is oxygen is an atom. However, O2 is a molecule, because again, a molecule is made up of two or more atoms, like oxygen. Oxygen plus oxygen would be a molecule like O2. Another question: which four atoms makes up 96% of living matter? Nitrogen, hydrogen, carbon, and oxygen. Nitrogen, hydrogen, carbon, and oxygen. Okay, another question: what does each atom's nucleus contain? We know what an atom is made up of: protons, neutrons, and electrons. But what specifically is inside just the nucleus? And the answer is protons and neutrons. And then what orbits around the nucleus? Those are the electrons. Another question: what is the atomic number and the atomic mass of this particular atom? So you don't have to know what this atom is. You just have to know what the definition of atomic number and the definition of atomic mass. And the answer is, all you have to do is add up the number of protons, and in this case, this particular atom has 6 atoms, and therefore it has an atomic number of 6. What is the atomic mass? All you have to do is add up the 6 protons plus the 6 neutrons, and actually the 6 electrons. 6 plus 6 is 12, and a little bit more for the electrons, so it's going to be just over 12. And if you want to know specifically what that is, let's move over to our periodic table. Let's see here. 6, all you have to do is find the number 6, because this is the atomic number here. And never mind. This particular chart doesn't give the entire atomic mass, but as you see up here, if we look at helium, 2 protons, the atomic number is the number of protons inside. 2 protons plus 2 neutrons plus 2 electrons right here would give us 2 plus 2, and here is the number of electrons. Here is the mass of the electrons, and that would give us 4.003. Okay, how about another question here? So what is the atomic mass? Add up the protons, add up the neutrons, add up the electrons. Everything all together. 12 point something with a something at the end. How many protons, neutrons, and electrons are we talking about here? 6 protons, 6 neutrons, and 6 electrons hovering around the nucleus. Okay, another question. Which orbital shell, if any, is full? Well, what's an orbital shell? Here's orbital shell number 1, where electrons are hovering. Another second orbital shell, and you just keep going and going. Since this particular atom only has 6, the only orbital shell that is full is the first one. How do you figure? Because the first orbital shell holds only up to 2 electrons. The second orbital shell holds up to 8. The third orbital shell holds up to 8. The fourth orbital shell holds up to 8, and so on. 2, 8, 8, 8, 8. So only the first orbital shell is completely full. The second one is not full. It only contains, this particular atom only contains 4 electrons in the second orbital shell. Therefore, it can actually hold up to another 4. Another question. How many valence electrons does this particular atom have? Valence electrons. Very important word to remember. The valence electrons, by definition, are the electrons in the outermost shell. So how many valence electrons? There are, in this particular atom, there are only 4, because the valence electrons are the electrons hovering in the outermost shell. 4. How many electrons does it have total? Well, 2 plus 4, 6 electrons. Well, is it reactive or is it inert? Is this atom reactive or is it inert? Well, the question is, really what we want to know is, if the atom has in its outermost shell a full set of electrons, in this case this would be 8 electrons in the outermost ring, then it would be inert. However, it doesn't have a full set. It can actually react another 1, 2, 3, 4 more times. This atom is said to be reactive because it doesn't have a full set of electrons in its outermost shell. It should, in order to be inert, it would have 8 valence electrons for this particular atom. Let's look at lithium. Lithium has 2 orbital shells. How many electrons does lithium have in its outermost shell? Only 1. How many more can it hold? It can actually hold 7 more. So lithium is reactive. Beryllium is reactive. Boron is reactive. So is carbon, so is nitrogen, so is oxygen, even fluorine. Why? Because in the second orbital shell, as we know, the second orbital shell can hold up to 8, and this one has 2, 4, 6, 7. It can actually hold 1 more electron. Therefore, this atom is unstable. Fluorine is unstable. Fluorine is reactive because it can hold 1 more electron. However, neon is non-reactive. It is inert. It is an inert gas, a noble gas. It cannot react with any other atom. It's very happy, and so is argon. However, all of these other atoms are reactive because they don't have full amount of electrons in their outermost shell. Even sulfur, if you look, first orbital shell holds up to 2, and it has 2. Second orbital shell holds up to 8, and yes, it has 8. However, the third orbital shell holds up to 8, but sulfur has only, in its third orbital shell, 2, 4, 5, 6. So it's reactive. It can react with 2 more, it can gain 2 more electrons. Sulfur is reactive, just like all these other ones. What are some other synonyms for reactive? We could say not happy. How about non-reactive? We could say happy, non-reactive, inert. Non-reactive, stable. Reactive, like stable. Reactive atoms are stable atoms. Non-reactive atoms are stable, but reactive atoms are unstable. Okay, how can this particular atom gain energy? How do you gain energy? Not necessarily by adding electrons, but by these electrons jumping to outer shells. As you jump away from the nucleus, you have more potential energy and you hold more energy. If you heat this molecule up, if you heat it up, you're gaining energy. How exactly is it gaining? Because these electrons can actually jump. So what state of energy is this particular atom in? What state of energy? It's in the lowest state of energy, and that's how you see all of these examples. These are showing in the lowest state of energy, so that way we can count up the electrons easily. Every single first orbital shell, they all have 2. And so on. 2, 8, 8, 8, and so on. What is potential energy based on? The answer is, it's based on position, the position in space. For example, a ball at the top of a slide has a lot more potential energy than the ball when it's slid down the slide and rests on the ground. High potential energy, low potential energy down on the ground. Where you are in space matters. Just like a diver at the top of on the top of a diving board versus a diver down in the pool. The person down in the pool will have considerably less potential energy because they can't move much further down, except for down to the bottom of the actual pool surface. All right, another question. What exactly is a covalent bond? We hear that all the time, covalent bond. Covalent, it's in the word. Just look at the word, break up the word. Co means to share. Valent, there's that word, comes from valence electrons. Sharing the outermost electrons. What is it exactly is a covalent bond? It's a bond between 2 atoms that are sharing their electrons. If oxygen, which has 2, 3, 4, 5, 6, 7, 8 electrons, 8 protons, 8 neutrons, and 8 electrons. If oxygen is to share its electron with another molecule, that molecule will sort of gain an electron, but this molecule will also gain an electron. Let's take a look. The one on the left has 8, the one on the right has 8. But if they share, this one will actually have 9 electrons, and this one will also have 9, because they're both sharing one of each other's. 8 plus this one. This guy will gain 1, but this one on the left is not gonna give it up. They're only gonna share. So they both essentially gain 1 electron. This guy gains 1 from here, this guy gains 1 from here. 1, 2, 3, 4, 5, 6, 7, 8, plus he's gonna share this one. And this guy has 8, plus he's going to share 1 from this guy. So even though he's sharing this one and this one's sharing this one, they both gain 1 electron. So now the atom is going to be, now this molecule will be a little bit more stable. However, how many can the second shell hold up to? The answer is 8, 2, 8. But the total will be 9, 1, 2, 3, 4, 5, 6, 7, 8 plus 1 shared is 9. Actually, we could actually share 1 more. So this electron moves over and shares with this guy, and this one moves over and shares with this guy. So you won't have just 1 bond, you will have a double bond. And here's the shortcut term. This line is demonstrating 2 electrons being shared, and this line is demonstrating 2 electrons being shared. and here they are. These set and these set. Now this molecule will be much more stable because the outermost shell will now have a full set of electrons. 2, 4, 5, 6, plus the other 2 that it's going to share from this guy. 1, 2. And this the same way. One bond signified by a single line, a double bond signified by another line. Each line represents 2 shared electrons. A total of, this would be an example of a total of 4 shared electrons. Well, if we break up covalent into polar covalent and non-polar covalent, that's 2 types of covalent. We also have ionic and we also have hydrogen bonds. 4 different kinds of bonding. Well, what is happening here? We know it's covalent, but the question is it polar covalent or non-polar covalent? If the amount of sharing is equal, it's non-polar. How do you figure? The protons are pulling on the electrons around. This is the amount of gravity. The protons are pulling, and these protons are pulling all these electrons plus even some of these guys on this side. So if the gravity on this side is equal to the gravity on this side, the pulling will be equal and the molecule is said to be non-polar covalent. So all you have to do is add up the number of atoms of protons over here, and if they're the same as the protons over here, then they will pull on the electrons equally. So this molecule, O2, is a non-polar covalent bonded molecule. Non-polar covalent bonding. Now, water. Water consists of an oxygen molecule plus a hydrogen and another hydrogen. Hydrogen all by itself has 1 proton and 1 electron. Is this hydrogen atom stable or unstable? The answer is all by itself it's unstable. And the reason why is because in its outermost shell, which is just the first shell, it only has 1 electron, but it can hold up to 2. It wants to share with 1 more to make it stable. This guy is going to share his electrons, this guy is going to share his electrons, and this guy is going to share his electrons. And since they're going to share, the molecule is now considerably more stable. However, the gravity in the oxygen molecule is considerably stronger than the gravity in the hydrogen molecule. And because the oxygen has more gravity, it can pull these electrons just a little bit slightly closer to the nucleus because the molecule has slightly more gravity than these 2. This only consists of 1 proton, but this molecule consists of several more protons, pulling these electrons a little bit closer. And if you're going to pull electrons, negatively charged electrons, a little bit closer, that would make oxygen slightly negative. And if this guy is going to pull these 2 electrons closer, just ever so slightly to this oxygen, this atom here will automatically become slightly positive because these electrons are moving just ever so slightly away from this atom, making this atom positive, and this atom slightly negative. A partial negative and a partial positive. Does that make sense? Ionic. Ionic bonds don't occur by sharing but by completely giving away. Sodium doesn't want to share because it doesn't even want that one particular electron. It's way happier if it just gets rid of it completely, because if it gets rid of it completely, the outermost shell will be the second one, which will have 8, not a third one with just 1, or a third one with 2. It'll have just 2 orbital shells, and the second, both will be completely full with electrons. Therefore, it gives it completely away. It transfers its electron to a different atom. In this particular case, in this example, it's chlorine. And chlorine, on the same token, would be happier if it not shared, but just received an electron completely. And therefore, we always see reactions between sodium and chlorine, like in the sodium chloride salt. This is called ionic. Why? What does ionic mean? What is an ion? This molecule will then become, once the bond occurs, once the ionic bonds occur, this atom will become an ion, sodium ion, and this atom will become a sodium ion. An ion is a charged atom, positively charged or negatively charged. Either way, it becomes an ion. If I give an electron away, I give away something negative. If I give something negative, I become a little bit positive. If I gain an electron, like in this chlorine atom, if I gain an electron, I become a little bit more negative. I'm an ion, I'm a negatively charged ion in a positively charged ion. Positively charged ions are said to be cations, and negatively charged ions are said to be anions. This is an example of ionic bonding. Not sharing, but giving and receiving. Transferring of an electron 100% to a different atom, and receiving that electron 100% without any sharing. This is ionic bonding. Well, the fourth type of bond is the hydrogen bond. The hydrogen bond, be careful, is not within the molecule. It's not between this H and this O, this H and this O, or this H and this N. We already said what type of bond this is. This is covalent. And not just covalent, we know that this is polar covalent. However, because polar covalent bonds occur, this oxygen is slightly negative because it's going to pull this hydrogen's electron just ever so slightly closer to this oxygen, making it a little bit partial negative and making these hydrogens partially positive. And if it's partially negative and over here is partially positive, and another molecule close by is partially negative and on other areas of the molecule are partially positive, you'll have an attraction between the hydrogen and another atom of another molecule. That is hydrogen bonding between there. It's not very strong. As a matter of fact, it's the weakest of all the bonds. Hydrogen bonds are the weakest. But again, hydrogen bonding, it doesn't occur inside or within the molecule, but between molecules. Another question. What is salt in a cup of salt water considered? What is salt considered? The salt, the fancy word is, and you have to remember this, the salt is solute. What is water? Water is a solvent. And what is the salt-water mixture? It's a solution. All right. I'm going to expect you to know some examples of hydrophilic molecules and hydrophobic molecules. Water is definitely hydrophilic. Alcohol is hydrophilic. It mixes with water. Anything that mixes with water is hydrophilic because water itself is hydrophilic. Oils are hydrophobic, water-fearing. Dirt is hydrophobic. Fats, hydrophobic. Now on to acids and bases. The more protons you have, the more hydrogen ions you have, the more acidic the solution becomes. You see there's many more hydrogen atoms than there are hydroxides. The more hydroxide atoms you have, the more basic a solution is. So if you have some solution like carbonated water and it happens to have a pH of 4, would that make that solution an acid or a base? Well, if the pH scale is from 0 to 14 and 7 being neutral, 4 would make carbonated water acidic. A solution that has a pH of 9 would make that solution basic. Now on to the last piece, carbon. What makes a molecule organic? The molecule has to be a carbon chain, carbons with hydrogens, or multiple carbons in a row. Why is that important? Well, because carbon dioxide has carbon in it, but carbon dioxide is not organic. It's a non-organic molecule. You have to have multiple carbon chains, multiple carbons in the chain, or carbons with hydrogens. Like urea is an example of an organic molecule. All of these molecules, methane, ethane, propane, butane, all these molecules are examples of organic molecules because we see they have multiple carbons in a row and carbons with hydrogens. How many molecules does this carbon bind with? 1, 2, 3, 4. How many atoms does this carbon bind with? 4. 1, 2, 3, 4. Every single time it's 4 with carbon. 1, 2, 3, 4. How do we figure? Once again, because carbon has 4 valence electrons, and how many more carbons could fit in the outermost shell? If the shell number 2 can fit up to 8, 8 minus 4 leaves 4. So it can bind 4 more times, up to 4 different atoms. They don't always have to be hydrogen. They could be hydrogen and oxygen, for example, all kinds of different bindings. And that means that oxygen can bind up to 2, because 2 more electrons would make oxygen completely full. And that's why you always see O with either a double bond or binding 2 more times. For example, water. O, H2O, 1 hydrogen plus another hydrogen binding to water. Fats are also organic. Oils, lipids are organic molecules, as we'll see in the next chapter. If you have a really long carbon chain, this is called a hydrocarbon. This is one leg of a triglyceride. This is what it looks like. A triglyceride, a fatty acid. And if there are no double bonds like this or like this or like this top molecule is said to be saturated because it can't fit. It's saturated with hydrogens. It can't fit any more hydrogens into the molecule because there are no double bonds. This carbon is attached to 2 hydrogens. This one is attached to 2. This one is attached to 2. But if you go over here and you look at this carbon right here, this carbon actually only has one hydrogen attached to it. It has 4 bonds, but just one. You could actually put one more in there. And if you look at this carbon here, this one is attached to only one hydrogen. You can actually put another hydrogen. So in just this single double bond, you can actually hydrogenate it with 2 more hydrogens. That's why this molecule is a saturated molecule, but this molecule is an unsaturated molecule because you can put in more hydrogens. Anytime you see a molecule with double bonds like that, means that it's unsaturated, means that you could actually hydrogenate it with more hydrogens. Now, how can we tell the difference between a cis fatty acid and a trans fatty acid? We've heard of that before, trans fatty acids. What is the difference? How can we tell? All you have to do is you take any double bond and you put a line across the double bond just like that. You see that? There is the double bond, you put it across. Now, as you have it there, you're going to have a carbon chain on one side of the line and a carbon chain, the rest of the carbon chain, on the other side of the line. Some of the carbon chain is on one side, and if the rest of the carbon chain is on the same side of the line, it's said to be a cis isomer, or a cis molecule on the same side. However, like in this example, if this side of the chain is on one side of the line and the rest of the chain crosses the double bond or crosses this line, that would make this fatty acid a trans fatty acid because it has crossed the double bond, like in this example. Now we're almost done with this chapter. Almost done. Your job is to memorize each of these functional groups. Functional groups are like flags on large molecules. And that's why each of these functional groups has a line, has like a dash, because it attaches to a larger molecule. For example, here's a large molecule, and here's the functional group, and it attaches to this larger molecule. Here's another functional group. This is a phosphate group, and it's like a little flag that attaches to the larger molecule. A little flag, a little flag, a little flag. So your job is to memorize these 7 functional groups. Hydroxide, the hydroxyl group, carbonyl group, carboxyl group, amino group, and so on. You have to memorize the name and memorize the shape. OH, CO, COOH, COOH, NH2, and so on. These functional groups make any particular molecule do a different type of job. If you add on any functional group to a different place on a molecule, the molecule itself will have a different job, will undergo a different function. And that's why they're called functional groups. They make the molecule that it attaches to do something and could do something different depending on where you add the flag or the functional group. Here they are zoomed in. Okay, ATP. We hear that a lot, and you'll hear that a lot in the future. Adenosine triphosphate. Adenosine is a part of this molecule. It's a purine, adenosine. And the triphosphate stands for having 3 functional groups attached to each other, and then the last one attached to adenosine. Phosphate, phosphate, phosphate. We bring up this particular molecule because it's an important high energy yielding molecule, and this will come up again and again in the second unit when we start talking about energy. Molecules contain energy for our purposes in the bonds between the atoms. In the bonds between atoms is where the energy is stored for our purposes. It's not 100% accurate, but it's pretty dang close. So that means the larger the molecule, the more energy it contains. And if you break the bond between any of the two, you get out a little bit of energy, and you can use that energy for something else. This is ATP, and if you break a bond, what's left over is adenosine diphosphate, and if you break it out again, you'll have adenosine monophosphate, and so on. And that concludes the first chapter.